So, we all hear about the incredible promise of quantum computers, right? How they're going to solve problems we can't even dream of tackling today. But here's the dirty secret: they're unbelievably noisy. They make a ton of mistakes. It's kind of like trying to build a supercomputer with faulty wiring. So, the real question is, how do you get a reliable answer from a fundamentally unreliable machine? Today, we're going to dig into the two main strategies for taming that quantum noise. Do you build a fortress to protect your data? Or do you hire a detective to find the truth after the crime has already been committed? Here's how we're going to break it all down. First, we'll get to know the enemy, quantum noise itself. Then we'll introduce our two main players, the fortress, which is error correction, and the detective, which is error mitigation. After that, we'll see how they stack up against each other, head to head. And finally, we'll take a peek inside the quantum developer's toolbox to see the actual software that's being used to fight this battle right now.
Okay, so before we jump into the solutions, we really have to get a handle on the problem. I mean, why is it so incredibly hard to get a quantum computer to just work correctly, consistently?
This quote right here just nails it. A quantum computer's amazing power comes from these super delicate quantum states, but that's also its greatest weakness. The tiniest disturbance from the outside world, something called decoherence, can cause a qubit to basically forget what it was doing. Seriously, it's like trying to solve a huge math problem on a whiteboard that just randomly starts erasing itself.
And that brings us to where we are right now, what everyone calls the NISQ era. It stands for Noisy Intermediate Scale Quantum. You can think of it like this. Our quantum machines are finally big enough to do some really interesting stuff, but they're still way too noisy to be perfect. So, in this NISQ era, dealing with errors, well, it isn't just some side quest, it's the main quest. It's literally the difference between having a revolutionary new tool and just a very expensive science project.
And the enemy? It's everywhere. The noise can come from tiny microscopic flaws in the hardware itself, little fluctuations in heat, vibrations, stray radio waves flying around, even cosmic rays zapping down from outer space. And on top of all that, the qubits themselves can start interfering with each other when they're not supposed to. That's a problem we call crosstalk. It is a constant, relentless battle just to keep the quantum information pure.
So how do we fight back? Well, our first strategy is the big one, the long-term, gold standard solution: quantum error correction, or QEC for short. The best way to think about this is like trying to build an absolutely impenetrable digital fortress around your precious quantum data.
The whole philosophy here is active defense. QEC is like having guards on patrol 24/7 inside your computer. It's designed to work continuously in real time, finding and squashing errors as soon as they pop up. The end goal, the dream, is a fully fault-tolerant machine. That's where your protected information, what we call a logical qubit, is way, way more stable than any of the individual, flimsy physical qubits it's built from. So let's walk through how this fortress actually works. First up is encoding. You take your one important piece of information and you spread it out across many physical qubits. Think of it like making a bunch of copies of your house key. Then comes syndrome measurement. You use these special helper qubits to constantly check on the main ones. Now, the really clever part is that this check tells you if and where an error happened, but it does it without ever actually looking at the data itself, so you don't mess up the calculation. This error report, the syndrome, gets sent over to a regular classical computer, which acts like a medic, figures out what went wrong, and sends back the right fix. And this cycle just repeats over and over again, protecting the data the whole time.
But here's the thing. Building that fortress, that takes a massive amount of resources. So for where we are right now, in the NISQ era, we have a much more down-to-earth approach: quantum error mitigation, or QEM. If QEC is the fortress, then QEM is the clever detective who shows up after the crime to piece together what really happened.
You see, the goal of QEM is totally different. It just accepts the fact that every single run of the quantum computer is gonna be noisy. It doesn't even try to fix errors while they're happening. Instead, you just run your quantum circuit a whole bunch of times, collect all of the messy, noisy results, and then you use some smart statistical tricks on a classical computer to figure out what the ideal, perfect, noise-free answer probably would have been.
Okay, check this out. This graph really shows the magic of QEM at work. See that orange curve? Those are our raw, noisy results. You can see its average is pretty far off from the true answer, which is that red arrow. Now QEM crunches that data and gives us the blue curve. Notice two things here. First, its peak is now dead on target. We fixed the bias. But you'll also notice the curve is wider, which means there's a bigger spread in the results.
It's a trade-off, right? We're sacrificing a little bit of precision to gain a whole lot of accuracy, getting us much, much closer to the right answer.
Okay, so we've got the fortress versus the detective. Let's put these two strategies right next to each other and see how they really compare.
This table really lays out the biggest differences. Look at the overhead trade-off. For QEC, you need a ton of extra physical qubits just to protect one logical qubit. QEM, on the other hand, is way cheaper on qubits, but you pay for it in a different way. You have to run your circuit over and over and over again. Another huge difference is the error rate. QEC only works if your hardware is already really, really good, below a specific error threshold. QEM can give you better answers even on today's noisier machines. And that's exactly why QEC is the long-term dream, but QEM is the essential tool that we absolutely need to get useful results today.
Now, none of this is just theory sitting in a textbook. Developers in the real world are actively building algorithms and fighting noise, and they're using a whole ecosystem of powerful software tools to do it. So, what's actually in their toolbox? This whole software scene is just exploding right now. At the very bottom layer, you've got your main SDKs like Qiskit, Cirq, and PennyLane, which you use to build your quantum circuits. Then you've got specialized tools for specific jobs. If you need to simulate noise really fast and at a huge scale, you do something like STEM. If you're building that QEC fortress, you need powerful decoder libraries like PyMatching to make sense of all the error signals. And if you're playing detective with QEM, you've got toolkits like Mitigation that are built specifically to make all that statistical analysis way easier. There's really a tool for every single part of this error-fighting process. So, this all leaves us with a really big question for the future of quantum computing. As our hardware gets better and better, do we put all of our energy into building these perfect, impenetrable QEC fortresses? Or will there always be a need for the clever, efficient detective work of QEM? Maybe the real path forward is some kind of partnership between the two. Figuring that out is what's going to define the entire next era of quantum computing.